if you ask anyone who's been in CS for long enough, how important are vectors, they'll probably say they are very important. Trust me, I would know. From graphics rendering to game development to even machine learning, vectors are very important. And it would be wise for us to learn how to basically multiply vectors. After all, they are very important. So there are a few ways we can multiply vectors. And of course, the two most used and important way is dot product and the cross product. So we will show how to calculate and compute these products in this video. First, let's start with the dot product since it's the easiest. The dot product comes from the operator symbol, which is just a dot here, just like that, a dot. And of course, on either side of the dot is some vectors. So you have a vector A and a vector B. So there are two definitions of the dot product, of course, or two ways to calculate them. First is the more geometric way. You've probably seen this in your high school physics class when you're dealing with stuff like work and calculating the force and the distance. So there's one way of defining this. So let's imagine this to be A and this vector to be B. Now they form an angle theta, of course, on the coordinate system. So that just equals A, so the magnitude of A, times the magnitude of B. Keep in mind the magnitude is a scalar, and times cosine theta. So you might have seen that definition. So again, one way of defining dot product, but we're not going to use that in computer science because oftentimes in computer science, you'll deal with dimensions over 1,000 or even 1,000,000. So how can you visualize that even on like a 2D or 3D world? Well, the obvious answer is you can't. So we can't really find a reliable cosine theta here. So we need to use another method to calculate the dot product. And here I introduce you the general way to compute a dot product. And of course, that is using the summation formula. So here we have a sum from k equals to 0 because we're computer scientists, up all the way up to n, and then we'll do a of k, b of k. So n right here is the size of the vectors a and b, and the size of them must equal, because if n changes, then you'll see why in a second, the dot product won't work. So we take the index elements, we multiply them together, and then we sum them all up. And that's why the dot product's nickname is a scalar product, because it returns just a number. So let's expand this summation out here. This just equals a of 0, b of 0, plus a of 1, b of 1, plus a of 2, b of 2, plus, you get the point, all the way up to a of n minus 1, b of n minus 1. And I'm kind of running out of room here. So let us go down here a little bit. So that is kind of like your general formula right here. What we're going to do is a simple example to demonstrate. So we have some column vectors here. So we have like 2, 3, 0. And we're going to dot that dot product with another, again, column vector. 5, 7. I'm just making up random numbers. 1. So you notice they do have the same amount of elements, because if they don't, we will not be able to sum them because whatever's going on here won't work. So we need, obviously, to have the same elements. So let us walk through this step by step. First, we start with the index k equals 0. So that is this right here. So 2 and 5, of course, equals 10. So write 10 down, and then plus, because we're summing this whole thing. And then next, we move down a index here. So the second row, or I guess the index row number 1, is 3 times 7, and that of course is 21. And then finally, this last row here, 0 times 1 is 0. So we can just write that down right here. So 10 plus 21 plus 0, what does that equal? Well, of course, that equals 31. So that is the dot product of this simple vector, or two vectors, I guess. you can see the dot product's not that bad to calculate, and it's even easier to calculate once we write this in C. So here I am in my handy dandy Linux terminal. You can do this with me with any text editor. Obviously, if you need a C compiler, you can go ahead and download that right now. Just pause the video. But if you got all of that set, come do this with me. Open up your favorite text editor and then create a file called .product.c. So we are going to write how we can compute the dot product in C, of course. And first of all, we are going to include our standard libraries here. So stdlib and stdio for printing. And then remember, the dot product returns a scalar value, so just a number. In C, we can get some precision with that number because oftentimes we don't want it getting truncated. So let's use a float for that. And then we're just going to create a function here. So first, we're going to pass in 2 pointers here. So first pointer is vector A, float, and then second pointer here is float vector B. So these will be the float arrays that we're passing in. And again, that's just the vectors. And then we need to pass in the size of these vectors since C doesn't really know the size of a pointer during compile time. So we can just do size of A and int size of B. So there you go. That is our signature for our function. First thing we're going to do a simple if statement. So if size A does not equal size B, then what we're going to do is we are going to write something in the console here. Actually, let's just do, yeah. So let's write vector sizes must match. And then we are going to return 0.0 divided by 0.0. Now, this is just a simple way to return a NaN, not a number. So this just basically tells our user here that don't ignore the return value, since we had to return something, but you know it doesn't work. And so now that we have that out of the way, the sizes are of course equal. So let us define our result here. So we can define a float sum result. We set that to equal 0. This will be our sum, and then we can define a just a basic for loop. So for I equals 0, I less than, we can pick any size A would do since they're both equal. And then we can do just the incrementer here. And yes, I am using a for loop. Again, this is a case of you can optimize it with AVX extensions and whatnot. But for the purposes of this video and for the sake of simplicity, for loop it is. Alright, so we are just going to do a for loop. So we're going to take the sum result and we're going to do plus equals vector A of I, again, just like what we said, I guess we could have named the K, times vector B of I, and then that's essentially what we're doing with our summation back when I was talking about the general formula. And then, of course, we are done. So return sum result and finish this out. Get a main function here. So let's define our float arrays here. So let's simulate our original thing where we had 2, 3, 0, and then our other float array will be again our example previously, which is 5, 7, 1. So these are again the vectors that I calculated by hand. So let's just make sure that our code works. So now what we're going to do is we could do size of A divided by size of, you know, A of 0, but for the time purposes, I'm just going to manually give the size. So let's do int or should I say float dot product result equals dot A. We pass in A and B as the vectors, and then we know that both of them have size of 3. Now what we do is we do print. We just print out the thing. How about 3 3 decimal places will work, even though this wouldn't require 3 decimal places, but just for record, we can get by with the int array, I know, but let's just do a float array. All right, and I think we are done. Actually, let's be a little bit more idiomatic here. Return 0, and then, of course, we are done. So now let us run this thing. So what we're going to do is I'm going to use GCC, passing the O2. We can get by with optimization level of 2. .prod.c, and then we can just straight up execute that binary it generates. So all in one fell swoop. Actually, what I'm going to do, just for the sake of simplicity here, is I'm going to go back up here, and then I'm going to add in a new line because I forgot about that. But yeah, so now what I'm going to do is save that and then go back down here. And of course, I did something with the case. This is why we need to be consistent with our cases, because this is a capital A, so we need a lowercase a. I don't know why I typed capital A and B, because my size values are all lowercase. Let's just keep it in all lowercase to prevent the confusion that happened. But yeah, so let's save this again. Go back down here, run this again, and 31. Would you look at that? So yes, it does work. Now let's go back up to our main function here, and then we are going to say we are going to change the value. Say B only has 2 values, so we just remove this one, right? Let's see what will happen here. Let's see if our code will catch and make sure that we don't get like a seg fault or something like that. So yeah, so hopefully that will work. Let's go down here again, and you can see vector sizes must match, and then it returns an NaN, which is good because it tells the user, hey, something's wrong. This won't return a number. You gotta fix your code. So yeah, that is a dot product. Hopefully you can see through some very basic code we can emulate a dot product in C and do it very easily. Now let's go to the cross product. So the cross product, otherwise known as the vector product, hint hint, can you guess what it returns? Link that in the comments below. But the cross product is a bit more complicated than the dot product, but I'll try to explain it with a geometric visualization just like earlier. Because the dot product only works in 3-dimensional space. Yes, I am aware there are 7-dimensional cross products, but I'm not going to get into what that is. Trust me, you do not want to know. So let's just stick with 3-dimensional cross products. So what is a cross product? Well, let's imagine our vectors here again. So I'm just going to draw vector A here and then vector B here. So now imagine this vector A and B, they're at a right angle. I know it's 2D on 3D art on 2D, and yeah, it's a bit hard to visualize, but imagine that as the right angle and we're looking at like a flat plane, right? And then the cross product creates a vector that's both perpendicular to A and B. So orthogonal to A and B up here, there you go. And then so now we have a right angle forming here and forming here. So this is the cross product. Yes, it is represented again with a cross sign. That is the vector of A cross B. So we can visualize this furthermore by defining some unit vectors here. So we can define I to be a unit vector in the direction of x. So if you're using x, y, z, that's kind of like what you're doing. So j is another unit vector that is in the y direction. So 0, 1, 0. And finally, k is another unit vector in the z direction. So now envision this in your head. What is I cross j? Well, of course, that just equals k, because we have a x directional vector here. So, whoa, what just happened there? Okay, x directional vector I, and then y directional vector unit vector j. Now, what happens to the perpendicular one? Well, of course, that is k. So hopefully you can kind of see where the cross product is coming from and why it's only exclusive to 3 dimensions. Because we need to basically visualize this thing where it generates a perpendicular vector to both the first operand and the second operand. So that is a basic example, but let's see how we can actually calculate this. So I'm going to represent everything in terms of unit vectors because it makes sense not just to write a bunch of column vectors. So here's what I'm going to do. I'm going to write A as 4i plus 3j minus 2k. So this again, 4 magnitude in the x direction, 3 magnitude in the y direction, 2 magnitude in the z direction. Again, same thing when you're multiplying by the unit vectors. And finally, b, I will define that to be 5i minus 2j plus 3k. So here we have, just two 3D vectors here, and again, you can visualize them by drawing it out or whatever. But just know that we're going to have a vector that is perpendicular to both of them, just like how I described it up here with this diagram right here. So you can see A is pointing that way, B is pointing this way, and then A cross B is pointing both perpendicular to them. So let's go down here and see how we can calculate this. We're going to use a 3x3 determinant, and this is going to be notation abuse because determinants can't have vectors inside of them. But just as, again, notation, kind of like a simple trick to calculating the cross product, we are going to do this. So if you hate me abusing notation, look away now, because I am going to abuse notation here. So here we have a 3x3 determinant with, again, I, j, and k, the unit vectors, as the first row there. So I know it's a bit bad to look at. But first, with that out of the way, let's write a here. So a is 4, just the magnitude. So 4, 3, and negative 2. And then let's write b in the last row here. So 5, negative 2, and 3. So we kind of get this gigantic, monstrous looking determinant thing. And here's the reason why I abuse this notation. Here is an easy way to calculate this. First, let's review how to calculate a 2x2 determinant, because we are going to need to calculate that as well. So you imagine 2x2 determinant of a matrix A, B, C, D. And this just equals AD minus BC. So it's the equivalent of this and then minus this. So AD BC. So that is a 2x2 determinant. Now let's go back to our 3x3 determinant. Well, how will we do that? And that is where this handy dandy tool comes in. So let's take a look at how we can do this. First, we are going to solve for what goes in the first I value. So I is, of course, right here, and I is going to not look at its own column. Yes, so no 4 or 5. X, bye-bye, you are gone. So no 4 or 5. And of course, the rest, if we highlight all of this, becomes a 2x2 matrix. Aha! So now we can do the formula we applied below right here. We can say AD minus BC. So in this case, AD is 3 times 3, so 9. And BC is 4. Negative 2 times negative 2 is 4. And again, if you're just wondering, 3 times 3 minus 2 times 2. So 9 minus 4, because that is what we want. So 9 minus 4, actually, let's just do that for now. And then we wrap that around with I, because that belongs to the I component. Okay, now, next thing we're going to do is, instead of adding, we're going to subtract j. So the j component, whatever we do in the j component, we will ultimately subtract it. So j, let's look at how j works. So j right here, again, we will ignore whatever's in its current column. So that leaves a 2 by 2 matrix again with 4 and 5 and -2 and 3. Imagine combining them. Of course, we get 4 times 3, and that's 12. So we write 12 minus -2 times 5. But remember, -2 times 5 is -10, minus 10 equals plus 10, because minus -10, sorry. And that, again, is j. And we are done. Now, for k, we're going to flip back to our good old friend, the plus sign here. So we're going to do a plus k here. So take a look at k right here. And then, again, we don't like the current column, so we look at the other two, and that creates, again, a 2 by 2 matrix. So 4 times -2 is, of course, -8, minus 3 times 5 is 15, so that is k. Now, just some final simplifications. I'm kind of, again, running out of room here again. This whole thing equals, well, 9 minus 4, 5i, of course, minus 12 plus 10 is 32, so minus 32j, and then, of course, -8 minus -15 equals -23, so -23k. And we have done it. This vector right here, 5i, 32j, -32j, -23k, is the perpendicular vector to both these two vectors right here. So I think that is pretty cool. I don't know about you, but that is how we, of course, calculate the cross product. So how about let's calculate this in C. Oh, just a quick clarification. Sorry about that. This is 22. My brain is not working today. Sometimes it's the most basics of math that get you. So before we continue, again, 12 plus 10 is 22. I promise I did not have 2 hours of sleep yesterday. Alright, back to our handy Linux terminal here. We're going to create a cross product calculator in C to prevent the mistakes that happened, of course, earlier. And again, that is why I want to do some C programming, because let's make the computer do the hard work. So, of course, include, again, the standard routine here. And then, here's what we're going to do. Since the cross product is only defined or at least for our purposes in 3 dimensions, let's just create a struct. So we're just going to do type def struct, and then we're going to pass in a float x, float y, float z, and then we're going to just call it vec3 or something. Okay, now since the cross product, also known as the vector product, if you guess correctly in the comments that it returns a vector, then again, it returns a vector, so we need to do that. So cross vec3a, vec3b. And that is it. Now, what we're going to do is we are going to define how this works. Actually, so what I'm going to do, again, there is ways to optimize this, but I'm going to showcase this for those of you who are just learning what the cross product is. So what I'm going to do is I'm going to do a result here. So vec3 result. I'm just going to just declare that. And result dot x, or should I, that x equals, and we're going to define a determinant here. So we're going to pass in the determinant. Remember, x is associated with I because that's the unit vector. So it will just be a dot y, a dot z, b dot y, b dot z. Because we're ignoring, again, think about the columns and how all that works. If you forgot how that works, just rewind the video, I'll explain it. And result y is a dot x, b dot z, because we're ignoring our current column. And then a dot, what am I saying? A dot z, b dot x, and b dot z. There we go. See, I told you again. With this is why we want computers to help us here, because I am not going to be reliable when doing hand calculations of the cross product. It gets pretty confusing, especially when you combine all of this. So again, ignoring the column a dot x, a dot y, b dot x, b dot y, and then we can return result. Finally, up here, let's define our determinant. Our determinant will compute a float for us. So float determinant, float A, float B, float C. Again, remember back to my definition here. It's just return A dot D or dot D. A multiply times D minus B times C. It is getting late. I don't know what I'm saying anymore. The video is getting pretty long. Anyways, let's just continue and finish this off. So, cross product done. Determinant done. Okay, main function. Here we go. So, let's define our float arrays. Actually, scratch that. We're going to use our vec3 values here. So vec3 A, we're going to initialize that to be, what is our thing here? So let's see here. From our previous example that I messed up on, 4, 3, -2. Okay, so 4, 3, -2. That is our first vector. Second vector is, let's see, 5, -2, 3. 5, -2, 3. All right. Now let's do result, or should I, yeah. Vec3 result equals to cross A and B. Printf. Okay, this time we're going to do it 3 times here. So let's actually format this a little bit. So this is just another way of formatting a vector. This becomes row-wise vector, but again, we're just we didn't do anything other than just swap the rows and columns, transposing it. New line, and then what we want, result.x, result.y, result.z. So again, 3-dimensional cross product, very useful because it is used in game design, especially 3D games, calculating the vectors and stuff. So very, very useful indeed. All right, let's see. Let's compile our thing. Cross prod. Let's see. Make sure to have a full cup of coffee when doing this, because I am okay. There we go. What did I do here? Should be 20, -23. Maybe we did something wrong with our. Let's go back and debug, because this just proves that I am not scripting these videos. I'm doing this live with you. And of course, there is our problem. Why are we summing it with b.z? I told you, it is late in the day. All right, so b.z right here, right? So there we go. So b.y, it's supposed to be b.y. Yep, that looks about good to me. And trust me, these Vim commands aren't really helping either. All right, let's write on the other hand. And there we go. 5, 22, -23, that's what we calculated. And just to prove our intuitions, again, sanity check, let's go back up to our vector values. We're going to edit this time so that A will be I and B will be J, our unit vectors. Because remember, I is in the direction of I, or X, I should say, and of course j is in the direction of y. So remember, I is going to be 1, 0, and 0, and for j it's going to be 0, 1, 0. It should return 0, 0, 1 because again the third dimensional component perpendicular to both of them of course is k, and that's 0, 0, 1. So yeah, let's just hope for the best, and hopefully I done my thing correctly. And of course I forgot to change this. So many mistakes in this video, but hopefully you can see that uh, sleep is important, guys, because this is what happens if you're sleep deprived. Woohoo! Let us have some sleep paralysis. All right, let's run this. And you can see 001 is what we expected here from our definition of cross product. All right, man, that was a long video, over half an hour. If you see, you can see dot product very easy, cross product not so much, and you need to be careful with your determinants and keeping track of your mental math, because if you don't, you're gonna end up having some errors, as you can see on the screen here. But anyways, hopefully you learn what these products mean and how to compute them and how they are used in computer science. If you enjoyed this video, please leave a like and subscribe, and hopefully I will go over in the future how to optimize these two functions in C with again SIMD and maybe some AVX extensions. So if you enjoyed this video, please leave a like and subscribe, and I'll see you in the next one. Thank you very much.